first of all, most important, an EBE student is missing. I put up the missing person alert on our Padlet. His name's Emmanuel, and he hasn't contacted his family. Haven't heard from him since last year. However, he has been at UCT because he used UCT accommodation up until February. And so I think on this announcement it says he was last seen the 27th of March. That's about 2 weeks ago. So there's a missing person alert out for him. If you know him or know anything about him, please, there are contact details on that announcement. It says that he suffers from severe depression, so I hope he's okay. Second announcement, well, that was the most important, but then after that it's just sort of admin things. Thursday afternoon tutorial, we finally have a good venue. We have Snape 4B. Okay, so everybody go to 4B, Snape 4B. All the tutors will be there. That took a week's worth of detective work and negotiation and being passed from convener to convener. In the end, it was a chemistry. It was a third-year chemistry course that had 4B. So it's just funny, I should tell you. So we've been using 4C. 4C was booked for a civil engineering course. So I contact the civil engineering course convener and say, why aren't you using your venue? And he says, oh, we're supposed to be in 4C. Goodness me, I've been in 3B all this time. So then we find out who's supposed to be in 3B, and I contact them, another civil engineering course, and they say, goodness me, we were supposed to be in 3B. We've been in 4B all this time. So then I was trying to find who's supposed to be in 4B, and it was a third-year chemical engineering course who don't need the venue. They just, booked a 110-seater venue and haven't been using it. So managed to negotiate a change there. So there we go. Tuesday second period, those of you who have managed to come know that we've, for the last 2 weeks, have had a clash there. Our venue was basically just given to other people, even though we technically had it booked. And we have been assigned EM7, but only for Tuesday second period. So EM7 is the one just around the corner from my office, okay? So the other second periods we're still in M202, although the people who have taken Tuesday from us are wanting to take Wednesday from us as well. But so far we're holding strong. So EM7 on Tuesdays, and then final announcement. When did we do this? Was it last semester? Or was it the semester before? I think it was the semester before. We ran some whiteboard workshops in the evening. If you could please be quiet. They were in a residence. Were they in Baxter? And I think sometimes they were in James L. I'm not really sure. I actually wasn't involved. Anita was running it with Stefan. But there's been a request to please run whiteboard workshops again in the evenings. Okay, so basically just extra tutorials, extra contact time for this course. But I understand some other students have said, please, we're not res students, please don't hold them in the evenings and res because that's very hard for us. So Anita has asked me to ask you what days and times would be convenient, but that's a rather vague question to put to you. So I'm not quite sure how to collate answers. I could put up a poll on the Vula site, or you can just make suggestions to me now. Do you have a suggestion, non-res students, of when you might like an extra tutorial? Any suggestions? It would probably have to be, there won't be an afternoon free. How many of you have afternoons free? Maybe you do. Okay, let's just have a show of hands. Who of you have Monday afternoon free? And by afternoon, I mean 6th and 7th periods. Let's say 7th period, just for the sake of argument. Who of you have Monday 7th free? Okay. Who of you have Tuesday 7th free? 3 o'clock. 3 to 4. I'm just using that for the sake of argument, just to get a sense of who has free afternoons. Okay, Tuesday. Wednesday? Thursday? Friday? So I think Monday was the most with about 10 hands. So it probably would have to be later afternoon, which already is messing the non-res people around a bit. So I tell you what, I'll put up a poll on the Vula site, and I'll put in 8th and 9th periods. What would they be? 4 and 5. and people can say if they'd be interested. And then maybe what Stefan could do is he could do one at that time period and then one in the evenings at a raise. Yeah, I'll do that. I will do that. Okay, so I'll put some sort of poll, and it's not organized through me. Stefan does the tutoring and Anita does the administration. I'm just the voice. Okay, I think that's all my announcements. So let's move on. If you could please keep quiet. Please keep quiet. Okay, please keep quiet. Today we're starting chain rule and directional derivatives. But I want you to have a little bit of class time working on differentiability. So why don't you try number 97, and I will give you, I don't know, I'll try for 10 minutes, probably not quite as many as 10. Okay, you've had more than 10 minutes to work on 97, or whichever one you're working on. Where are we? That's the page. Please keep quiet. Please keep quiet. So this is a not particularly unusual test or exam question, except it probably wouldn't say show that f's not differentiable. I mean, it could, I suppose. It's more likely to leave it a little bit vague. Is the function continuous? Is it differentiable? Like if you look at the sort of wording of question 102, that's sort of a typical framing of a test or exam question. Okay. So I used the analogy, what did I use the analogy of? A horse or something? A horse, how fast the class is going. If doing this course is like riding a horse, it starts off kind of trotting. At the moment, it's going at quite a gallop. It'll slow down a little bit when we begin double integrals, and then it'll build up into a gallop again. So I know this course goes very fast, and there's just no option. There's just no option. Okay, let's talk about chain rule. Okay, we use the chain rule for composite functions. We use the chain rule when we have a function of a function. Single variable chain rule, you differentiate your outside function, leaving your inside function unchanged, and then you multiply by the derivative of the inside function. And chain rule in two variable functions is the same, except in this sort of typical manner, you end up getting extra terms, because when you talk about differentiating with respect to what variable, and suddenly you have all these multiple options, and you end up with your chain rule expression having lots of terms. Okay, so here we go. In fact, I think I put it in a box, didn't I? Yes. There's a big chain rule box on page 33, sorry, I beg your pardon, on page 33. And what I'm about to give you now is those formulas. If z is a function of two variables, and those variables are themselves functions of something else, helps if you plug it in. We're waiting for magic to happen. There we go. Lovely. Okay. Okay, starting again. If z is a function of two variables and x and y themselves are functions of some other variable implicitly, and if all of those functions are differentiable, then you can differentiate z with respect to t. Actually, let me be pedantic here. Okay, there I'm using ordinary d's. So z is a function of x and y are functions of t. So if t changes, x and y will change, and because x and y are changing, z will change. So z is explicitly a function of x and y, it's implicitly a function of t. And down at that level, z is a function of only one variable, t. If you're thinking at sort of one variable removed. And that's dz by dx times dx by dt plus dz by dy times dy by dt. And notice that mixture of d's there. Because when I differentiate z with respect to x and y, I should use a curly d because z is a function of two variables at that level. But meantime, x and y themselves are single variable functions, so they have ordinary d's. If you muck up your d's, it's not that big a deal. If you like to be an exact person who gets their notation right and their terminology right, and I hope you are, then do try and take notes. But it's not a train smash. Let's be quite pragmatic here. It's not something you're going to lose marks for. But you should try and be precise, particularly in a subject like mathematics. So do try to get them right. Okay, and then what if x and y were actually functions of two variables? Get the wording right. Here we go. If z is a function of two variables and x is a function of also two variables, and so is y, then we can differentiate z with respect to t, but we can also differentiate z with respect to s. Okay, and that's going to be dz by dx, dx by dt, plus dz by dy, dy by dt. And then the same here, except s's. There you go. And that should look, except for the fact that there's now an extra term, that should look familiar to you. That's chain rule. That's what you're doing when you do single variable chain rule, except with single variable chain rule you'd only have one of those terms. And you'd only have ordinary d's. But other than that, that's chain rule. So I hope that does look familiar to you. And then I want to go through a proof, but rather than write out the proof and then everybody copy it down, and then there's f's and there's t's and there's s's and there's h's and everybody's copying it down wrong, I've printed out the proof onto page 33, and I'd like to just talk through it. Okay, so if you have your handbooks open to page 33, to start off with, in that very first line, what you're basically doing is you're putting in the definition of the derivative. Okay, dz by dt is going to be the limit as h tends to 0 of, and you'll notice in the first term in the numerator, tell you what, I am going to do some writing, but it is all there in the box. So copy it down if you want, but I'd rather you copy it from the book than from my writing because you're less likely to make a mistake. So the proof, handbook, page 33, you start off with your definition of the derivative. This is the thing we want. We're wanting dz by dt. So I'm giving a proof of that the first chain rule formula. The definition of the derivative, it's the limit as h tends to 0 of f. Now it's not x plus h, okay? Because we're not, the thing that we're differentiating with respect to is t. So the thing that's changing is t. So we don't want an x plus h, we want a t plus h. So it's x of t plus h and y of t plus h minus f of x. I could just write xy, but I'm just going to write that. Okay, so the thing that's changing is the t, because it's dz by dt. And a derivative is all about how one thing changes as a result of another thing changing. So it's the t that's changing, and we want an expression for how z is changing. Okay, so then if you look, I'm not going to write this down, but if you look at the second line in the proof, in the box there, you'll see we've done, if you remember when you derived product rule, back in first year, when you derived product rule, you had a process that looked quite a lot like this. You had a product of two functions minus a product of two functions, and what you did was you added in a term in your numerator, but you also subtracted it out, where that term had something in common with the original first term and also something in common with the original second term, so that you were then able to take out some common factors and do a bit of grouping. Don't know whether you remember that, but that's exactly what's happening here. We are subtracting a term and then adding it in again, so really we're just adding 0. Mathematicians have lots of sneaky ways of adding 0 and timesing by 1. You can do some very powerful things by adding 0 and timesing by 1. And so by subtracting that term and then adding it in again, you're able to then chop that huge expression into two expressions, where in each of those expressions, it's either the x that's changing or it's the y that's changing. And with a little bit of manipulation, you can then achieve the final result. So in the first, when you've chopped it up, in your first expression, it's the x that's changing. And in your second expression, it's the y that's changing. If you look at the two terms in each of those numerators. Okay, but then for each of those limits that we have now, in that third line we have two limits. In each of those limits that we have in the third line of the proof, the thing that's in the denominator is not the thing that we really need in the denominator. The thing we need in the denominator, if you think of a typical difference quotient, so back in first year you would have had something like this. Okay, we all recognize this. Notice how this h here is what we have if those two things are subtracted. X plus h minus x. People are yawning. The thing that's at the bottom is the thing that you get when you subtract the two things that are changing in your numerator. So in those two limits that we get when we chop up that huge expression and we chop it up into two limits, the difference between the things that's changing at the top is not actually h. In the one case, it's x of t plus h minus x of t, and in the other one, it's y of t plus h minus y of t. So that's what we actually need in the denominator in order to interpret that expression as a difference quotient. So we just do that by timesing by 1. We times by the thing that we want in the denominator, top and bottom, and then just group the terms and group the terms isn't quite the right word here. We basically group that information in appropriate ways so that every single one of those expressions can be interpreted as a difference quotient, as a limit of a difference quotient, and as a derivative. Okay, so I want you to understand what's going on in that proof, because while there's lots of letters there on the page, it's actually quite a simple proof. I mean, yes, it's very busy. You look at it and there's y's and x's and t's. But if you actually just look at each line, it's quite clear to see what's happening from one line to the next. So this is one of these rare cases in this course where the proof is short and easy to understand. Because a lot of the things that we do, if I was to do a proof, it would take me the whole day. Or the whole lecture, not the whole day, the whole lecture. And so I choose not to because our time is too precious. But here is a rare case where the proof is quite nice. Okay, so I'm not going to do any more writing of the proof. We will not ask you to give a proof, but there you go. You're in a maths course, you should see some proofs. Yay, proofs! A proof of a theorem is a logical argument showing that a statement is true based on the truth of the statements that it's built on. And they're important. Proofs are the beating heart of mathematics. Okay, and then we just use the results. Okay. Oh no, don't yawn, jeez. Is there anything I want to say about chain rule before doing examples? Let me just look through my notes. That's an example. That's an example. Those are some examples. Right. Let's do some examples. Which ones do I want to do? Okay, I'm going to do number 104. What's the time? I've got 12 minutes. Right. I'm going to do number 104. Z equals x squared y cubed plus 3xy to the 5. X is sine t and y is cos 2t. Okay. So we've been given a function and now we need to differentiate it. So really this is just plug stuff into that formula. We know that dz by dt is dz by dx, dx by dt. Write down the formula first before you start putting things in so that it's something that you can keep referring back to instead of having to hold it in your head. Okay, so what is dz by dx? Let's have a look. It's 2xy cubed plus 3y to the 5. And dx by dt is cos t. Plus, what's dz by dy? It's 3x squared y squared plus 15xy to the 4. And then what's the derivative of y? It's negative 2 sine 2t. Oh, I'm going right to the edge of the page here. Negative 2 sine 2t. Bit of a squash. Okay, we now want to evaluate that when t equals pi over 6. But of course our derivative doesn't just have t's in it. It's got x's and y's in it. Now what you could do at this point is you could replace every x with sine t, and you could replace every y with cos 2t, and that would be fine. Would be messy, but it'd be fine. But you don't need to do that. What you can do is you can just work out what x at pi over 6 actually is. Let's have a look. Here's pi over 6, that's root 3, that's 1, that's 2. Sine of pi over 6 is a half. And y at pi over 6 is cos of pi over 3, which is also a half. Am I right? My memory is just remembering root 3's in this problem. But no, I think I'm right. Cos of pi over 3. Yes. Oh, I know why I'm remembering root 3's, because they come in into the over here. Is there a question?
Yeah, the first dz by dt, is that supposed to be curly d's or not curly d's?
No, everything that's got a t at the bottom in this problem has an ordinary d. Because you can kind of think of z as a function of x and y, but x and y are both functions of t. So if you're thinking of z as a function of t, if you're thinking of that sort of that implicit level, z is a function of only one variable, which of course is different if x and y were functions of s and t. But as I say, it's not a huge deal if you use curly d's. So what is this? This is 2 times a half cubed plus 3 times a half to the power 5 times cos of pi over 6. That's root 3 over 2. I knew I remembered root 3's. Plus, golly, 3 times a half squared times a half squared plus 15 times a half to the power 4 times minus 2 of sine of pi over 3, which is root 3 over 2. Okay, and then you multiply that out. And I must admit, it's a trifle hairy. That'll be 2 over 16 plus 3 over 32 times root 3 over 2 plus 4 times 4 is 16, so it's 3 over 16 plus 2 to the 4, 32, and that's 15, and that's I would like to say that we won't give you something like this in a test or an exam, but we might. I know the people who will have a lot of control over setting the tests and exams, and it's possible. So times by 2, that's a 4, so that's 7 over 32. I don't need brackets anymore. times root 3 over 2 plus times by 2, it's 6, it's 21 over 32 times minus root 3. So it's, so that's a 64. Okay, that's 7 root 3. And that would be minus, and I have to times it by 2, so it would be 42 root 3. And 7 minus 42 would be negative 35. Okay, so there was nothing hard there, right? Although, okay, all right, possibly the hardest part was doing fractions without a calculator. But the next hardest was probably memorizing the chain rule expression. But it's a very logical expression. The chain rule expressions, which are towards the top of that box on page 33, are very, very logical. So I find them very easy to remember. I don't need to put any work into it because it makes so much sense. Yes?
Would you mind talking through the first expression that you put up there in sort of like non-formulaic terms?
That top line over there.
The 2xy to 3, that first one.
I'm not exactly sure what you're asking for there by non-formulaic terms.
I mean, as in that we're not just plugging into the formula, but just where you draw things from the first stuff.
Like, what was your thought process?
So that we can do this without having to do the dz by dt dx plus dt like thinking.
Seriously not getting the question. So, what was my thought process? My thought process was, it's chain rule, okay? It's chain rule, so I have to use the chain rule formula. Because you're doing chain rules, so I'm not really sure what you're asking here. Let's hark back to single variable chain rule. Here's single variable, and everybody just keep calm. Here's single variable chain rule, all right? F of g of x, if you differentiate that, it's f dash of g of x times by g dash of x, okay? All right, so f, please keep quiet. So we're basically working out df by dx, and that's dg by dx, and that's df by dg. So that's chain rule. Chain rule says differentiate your outside function as if the inside function were the variable with respect to which you were differentiating, and then multiply by the derivative of the inside function. So that's single variable chain rule, and all we're doing is we're upping a variable because we're saying that f isn't just a function of g now, it's a function of two things. Well, before I used x and y.
So
Yeah?
I really like the way of thinking of the composition style, because I just think of like multiply by the derivative of the inner thing, and so I suppose that's what I'm meaning. If you could explain how you did the first time, if that's possible.
Let me think about it. Okay. So if that first thing, so when I'm teaching first years and I give chain rule in that top line, I say like I said it earlier, I said you differentiate your outside function, you multiply by the derivative of the inside function. So for the sake of the audio, I'm being asked to express multivariable chain rule in that same language. Okay, sure. You still differentiate the outside function, leaving the inside function unchanged. But the thing is that when you do that differentiation, you have the option of with respect to which variable you differentiate. So you differentiate, so you can't use the dash notation anymore. So if I have an f as a function of u and v, where u is a function of x and v is also a function of x, then I have to differentiate my outside function, but of course I have options. So I differentiate my outside function with respect. So f is a function of u and v are both functions of x. I'm trying to keep it in the same sort of language that I used over there. So I differentiate my outside function with respect to u. Sorry, that should be a u down there. And then I multiply by the derivative of u with respect to x. But then I need to add in another term. I need to differentiate my outside function with respect to v, and then I multiply by the derivative of the inside function. So that's what's happening. You're still differentiating your outside function and multiplying by the derivative of the inside function, but when you differentiate your outside function, you have a choice of variable, and each of those options gets a term of its own.
Sorry.
Yes.
Shouldn't that be f subscript x?
Thank you. I made a number of little slips over there. Let me just tidy that up because it's a bit ugly. Okay. Yes, sorry, that f of uv that I originally wrote was just me talking about my function, and then I repurposed the line, so I dropped it. I forgot to put the subscript in. Okay, so that's that. Here's a reason why this D notation is quite a handy notation. You can check yourself, see? That notation looks like fractions. It's not fractions, but its resemblance to fractions is non-accidental because it comes from a ratio, a delta something over a delta something, and the limit that the thing at the bottom tends to 0. So the resemblance of the D notation to fractions is not accidental, even though technically speaking that's not what they are. But if those were fractions, if those were actually fractions, you could cancel, couldn't you? Because we've got dz over dx, and we've got dx over dt, and if those were actually fractions, we could cancel the dx's. And in that term over there, we could cancel the dy's. And notice if we did that, the terms on the right would look the same as the terms on the term on the left. So if you're using that D notation, you can kind of check yourself. Because just quietly in the secrecy of your own head without telling anybody, you can pretend those are fractions and do some cancelling. And what you're left with on the right should be the terms that look the same as the one on the left. Now, they're not fractions. But if you just play that trick with the notation, you can check yourself. And if you don't end up with terms that look the same, then you're not using the formula properly. You're putting the wrong things in the wrong places. Okay, it's the end of the lecture. Is it a quick question? Okay, I think I'm going to have to return to this again tomorrow. Okay. Thank you very much. If you could send my registers back, that would be great. I'll return to chain rule tomorrow.